Hello, my name is Nasser Al-Duwaj. Sorry. I'll be talking about multi-mobile computing, or M2. Mobile systems have become ubiquitous with many users relying on multiple systems, but they are usually used in isolation and offer different experiences for users. However, there has been a growing demand to provide users with a seamless experience across multiple mobile systems, not just use them as separate individual ones. So instead of using them in isolation, we want to dynamically combine and mix all the functionality of multiple mobile systems into a more capable one for a better experience. Given the many popular apps out there, we can combine and mix them to do cool things with existing unmodified apps. We refer to this as multi-mobile computing. For example, imagine someone hosting a call on their smartphone. In a room full of their friends. Instead of everyone huddling over a single smartphone, everyone can instead provide their smartphone's microphone and speakers from anywhere in the room to be combined seamlessly on that single call. Or we can combine everyone's camera from different angles for a 3D picture or panoramic video to be taken. Users would do this even with their own favorite existing unmodified camera app. Here's a more concrete example. Using multi-mobile computing, we can take a single system, let's say playing Angry Birds here, and simply place it next to nearby systems to combine displays. These systems would automatically adjust to the number of systems and their locations in the grid to form a multi-headed display by combining all displays together without ever having to modify Angry Birds or having it run on all systems. This example can be used for gaming or watching videos instead of multiple users sharing a small screen. Users can move their systems around and place them randomly in a grid, and it will automatically adjust. Finally, instead of combining functionality, imagine being able to mix those functionalities. For example, many apps rely heavily on touchscreen for input control, such as camera apps, drone controller apps, or games. It would be great to be able to mix sensors with touchscreen functionality by using sensors to represent touchscreen input on another system. This enables us to use another smartphone as a controller, like a Nintendo Wii controller. By mixing functionality, we can turn an existing touchscreen-only app, such as a tennis game, to a full motion sensing game without ever modifying it. So in order to make multi-mobile computing possible, we need to combine and mix devices by sharing them. This means systems need to access remote devices and provide remote access to local devices. We also want to provide multi-mobile computing without requiring app modifications, as many apps can benefit from this. But there are key challenges. A major challenge of sharing devices is that mobile systems are highly heterogeneous. Users have different systems, as can be seen from this figure showing just Android's market share fragmentation. This makes it very difficult to share access to devices, as we can't just do straightforward things like forwarding calls. Each system likely has different devices with their own device-specific interfaces. Previous approaches have addressed sharing devices mostly in a one-to-one manner. By basically forwarding calls. These approaches do not easily work with heterogeneity and especially mixing devices, since they deal with specific vendor or platform device calls that they forward. So how do we solve this challenge if forwarding calls is not feasible? We first observed that device data on mobile systems provided to apps is generally in a standard or common format. For example, display data can be represented as H.264, microphone and speakers data is generally in PCM format, and apps receive generic device data, not low-level device vendor-specific data. We also observed that mobile systems are vertically integrated and provide a user space system services layer for communicating with devices. These system services are long-running system processes per device and handle device data in a common, non-vendor specific format. Instead of accessing devices directly, apps tend to interact with devices through these system services. Based on these observations and to solve these challenges, we introduce M2. M2 takes a device data approach that makes unmodified apps multimodal by allowing them to transparently share, combine, and mix devices. Having observed that device data is in a common format, M2 takes this data-centric approach. It exports and imports device data, not device calls, in a common format to and from systems. This allows M2 to not only do simple device sharing, but mix and combine devices of different types since it can aggregate or manipulate device data in a known format. To make all of this work, we first must give users control over what to share and which unmodified apps to share to. For that, we provide the M2 app, which runs on both Android and iOS. The app also provides security, authentication, and localization. But we still need a system to provide a system and another system to access that device. In the multi-headed display example, the unmodified app, Angry Birds, would be running on only one of these systems. And that system would need to access the displays, speakers on remote systems, providing access to those devices. Input needs to be provided by all systems and transparently shared to the unmodified app, Angry Birds. All systems here would be running the M2 app. So first, to provide a device for remote access by another system, we leverage the existing M2 app. Since mobile systems are vertically integrated, we can easily obtain or provide device data in a common format by using existing public APIs. So we just add that logic to the M2 app since it runs on every M2 system. Using just an app is beneficial for a few reasons. First, the device provider does not require architectural changes since the unmodified app is not even running on that system. All it needs is the M2 app in this case. For example, using existing public developer APIs, we can draw to the display and read sensor data simply through an app. Second, the app simplifies the process as the device data reaches the app layer ready for exporting or importing, and providing devices only requires running the M2 app. Last, using just an app for a device provider makes it more portable and cross-platform. So with an app, we can simply provide devices, but now we need to give an unmodified app access to that remote device data transparently. To do so, we revisit system services. First, recall that system services are long-running system processes that interact with hardware devices and exist per system, not per app. Second, apps access device data that is in a common format via system services. Last, system services control which device data goes to which app. So it really makes sense for M2 to intercept at this system services layer. To piece all of this together, we need a device provider on one side to import or export device data. On the system that accesses this remote device, the relevant system service is modified to also import and export common device data. The relevant system service can then export the device data provided by the unmodified app or import remote device data into the unmodified app. So to the unmodified apps, nothing changes. All devices are just local devices, even if they are actually remote devices. So an unmodified app can request sensor data and receive remote sensor data provided by the same system service, or play audio, and the audio would be intercepted by the system service and forwarded to a device provider. But to fully realize our goal of combining and mixing devices to provide multimodal computing, there are still a few challenges we have to overcome. Mobile systems differ in default specifications. For example, systems might have different display resolutions or might not even have a specific device like a pressure sensor or 3D touch. Apps are not designed to access different device types. For example, a tennis game that uses touchscreen for swings cannot simply work with sensors without modification. Finally, apps do not expect multiple remote devices from the same stream. M2 solves this challenge and fully enables combining and mixing devices by introducing device transformations. Device transformations allow for creating a virtual device that can be a combination of different devices that can appear as a single device called the fused device. This is like the multi-headed display, which uses a single fused display. It also enables representing a device as a different type, such as the sensor to touchscreen input example. These transformations are possible since we can easily manipulate or convert device data as it is in a common format. For example, the touchscreen input can be easily scaled. Display frames can be easily converted to camera frames or vice versa. This enables us to reinterpret or represent forward with forwarding device calls. Existing apps. M2 provides a plugin framework to allow for custom gets to the app. Information implementation prototype supports user-facing GPS, speakers, microphone, sensors, and iOS app implementation only supports providing devices and not accessing a remote device since we cannot modify the iOS frameworks. Our prototype was easily ported to run on multiple systems and OSs as shown here. M2 was ported to run on 6 different Android versions, 3 different iOS versions, and 6 different systems, smartphones, and tablets. Cross-porting the M2 app on different platforms was easy. The majority of the code for the M2 app was platform independent, with the exception of device data handling code. The total lines of code for the 7 modified system services was about 800, and the average was only 115 lines. To show the potential of multimodal computing, we made some apps that illustrate how it can be useful. Due to time constraints, I only discussed 3 of these apps. First, we simply provided iOS devices to Android through the iOS M2 app, allowing an iPhone 6s to effectively run unmodified iOS and Android apps from the same iOS system. Here's a video of the iOS M2 app seamlessly accessing both iOS and Android apps. We are accessing iOS apps here, and then switching to Android, where we can access Android apps like the Play Store, and then switching back to iOS, the App Store, and then back to Android, where we can even run graphics-intensive apps like this game. Second, we implemented the fused display input and audio scenario that can be automatically configured on the fly using M2's indoor localization feature. Using 4 Nexus 9s in a 2x2 grid, we designated one of them to access the remote displays and speakers and to receive remote input. The 3 other systems received display and audio and provided input. Aside from the bezel separation, our user study shows that the video for the fused scenario was well synchronized and visually indistinguishable from using a single local display. These Nexus 9s are much older and have a larger bezel. More modern systems have much smaller bezels, and they continue to decrease in size. The video here shows a 2x2 fused display with indoor localization activated. Placing the systems together automatically adjusts the display, and moving the systems around will readjust the grid automatically. Third, we used a device transformation from sensor data to input touches to provide a Wii-like experience for unmodified Android games such as 3D Tennis and Epic Swords 2. We used a transformation plugin to convert a remote smartphone sensor data to input touches where the game is running. For the Swords game, we used a left swing to represent a left swipe, and so forth. The game uses a V-motion swipe for a stab. Instead of this unintuitive action, we translated a forward hand gesture, similar to a stab, to this V-motion swipe. Our user study showed that using the controller was much more realistic and intuitive as a gaming experience than using the touchscreen. The video on the left shows a left swipe, right swipe, then the unintuitive V-motion swipe for a stab. The lag is due to the game itself, not M2. The video on the right shows the sensor to input transformation device instead, with a left swing, right swing, and the much more intuitive stab using a forward hand motion. We described more apps along with user studies in the paper. Finally, I discussed the performance measurements of the M2 prototype. We test multiple devices and scenarios in the paper, but due to time constraints, I only discuss the performance of display sharing since it is the most bandwidth-heavy device. We ran Passmark, a popular mobile benchmarking tool, on a Nexus 9 sharing its display. Passmark tested CPU, memory, disk, 2D and 3D graphics. I only show 3 of those scenarios which ran Passmark on a single Nexus 9 while sharing the display locally, then while sharing the display to 1 remote system, and finally while sharing the display to 3 remote systems in a fused display scenario. The display sharing was done at full resolution, 10 megabits per second bitrate and 30 FPS. The performance here is normalized to idle, which performed the same as stock Android. Lower is better. In general, the local or one case performed slightly better because it did not send frames out to the network. For Passmark CPU, disk, and memory tests, there wasn't a heavy performance hit compared to running multiple apps concurrently. The performance difference is due to M2's networking and copying of frames. Adding more devices does not have a significant increasing hit on performance. For Passmark's 2D and 3D graphics tests, there is an acceptable performance hit. The benchmark runs stress tests that are not typical of most apps. More importantly, if we ignore the local one test, the results show that adding more devices does not have a significant performance hit. M2's performance is really good even when running these intensive stress tests. I conclude this talk by pointing out the potential of multimodal computing. Our M2 system is easy to use and does not require app modifications. M2 supports a wide range of platforms and systems by sharing device data, not device calls. Furthermore, we introduced device transformations that can enhance and unlock new ways of interacting with existing apps. Finally, we demonstrated that M2 runs efficiently and scales well, especially compared to existing approaches. More apps and testing results along with implementation details are discussed in the